In this short video, we're going to look at the sensible heat recovery process on a site chart. What we mean by sensible heat recovery would be let's say a ventilation unit that's bringing outside air into the building and exhausting air from the building out, and there would be some device between the two air streams to recover the heat. This could be a rotor, this could be a plate, this could be a heat pipe, any of that kind of technology that allows you to move heat from one airstream to another. So we're going to start by looking at winter conditions, heating recovery. And so now we have two airstreams and we have two starting points. So let's start with our return air. It's over here. You can see it's 72 degree dry bulb. Now on a site chart, these conditions across the bottom in this light green are your dry bulb conditions here. So you can see this running up. This is at 72 degrees. We follow this up and you can see that the return air in the winter has 20% RH. Now that's what these lines are. These are these sweeping curves here, are relative humidity lines. So you can see 10, 50, 90. This line here, very important line, this is the saturation line. It's 100% RH. This means that the air cannot hold any more water vapor. It's completely saturated. So we've got a starting point for our warm return air to our ventilation unit in a winter application. Let's go find the outdoor air stream. So in this case, we're going to start with air that's at 0 degrees dry bulb. So you can see this is a low temperature psychometric chart, goes way out into the low end, and we're starting at 0 degrees Fahrenheit. This air is very close to saturation. Winter air does not hold very much humidity because it's cold. It's not capable of holding a lot of humidity, and so it's always very close to saturation, that being this curve here. So let's go ahead and add the processes in here. I'm going to start by looking at the return air. Now, law of conservation of energy says that any energy we take out of one airstream has to go into the other. And for the purpose of this example, we're going to assume that the airflow rates are exactly the same on both sides. You can do the calculations with different airflows, but it's easier if we start and just assume that whatever's coming into the building is also going out of the building. So we have this device, it could be a rotor, it could be a plate, and we are going to start to extract that heat out of the return air. And we'll see that as a drop in temperature, right? So that means you get a perfectly horizontal line like this, and you can see that we're crossing these green vertical lines here, which are the dry bulb temperatures. We started at 72, and there's 65, and here's 50 degrees, and we continue to extract that heat going along this way. Now, the device is taking that energy and putting it into the outdoor air. So we started at 0, so as this air goes this way and gets colder, the outdoor air is gaining that heat and is going this way and getting warmer. And so you can see it going from 0 degrees to 5 to 10 to 15 as it climbs up. Now we've put 32 degrees on the site chart because there's an important conversation to happen, and it's really around the return air. This return air has some humidity in it, right? We said it had 20% RH, so there are water molecules in it. And at some point, this horizontal line is going to be 100% saturated. And that's this line here. And you can see that it actually hit the saturation line just about 30 degrees, just below freezing. Well, that means if you want to take any more energy out of this air, you're going to have to start seeing condensation. That the first thing that's going to happen is that some of that water molecules that are in a gas form are going to have to turn into a liquid. But we're doing this process, that's going to happen below freezing. So this isn't just going to turn into a liquid. This is going to show up as frost on the heat recovery device. And so this is why you hear a lot of conversations about winter heat recovery, about how do you do frost control, because this device will actually start to have frost form on it. That will stop the heat transfer. It will actually block off the air passages. It's not acceptable to run that equipment. But if you just turn this device on and ran it with these conditions of 72 degree return air with 20% RH and 0 degrees and left it, for 15 or 20 minutes, this is what would happen. The air would start to frost. You would continue to take that energy out. That energy would be passed over here, and you could warm this outdoor air up to a pretty warm condition. but ultimately that frost will block off the device. And so this is not a stable operating condition. So it can happen short term, but is not something that can go along. There's a very clear example of what it means to frost energy or a heat recovery device. So what happens in the real world? In the real world, there is some form of frost control. If it was a wheel, a rotor, you would slow the rotor down or blend air around it. If it's a plate, well, most people would have an air bypass around it and be able to direct air around it. But they're basically modulating the capacity of the device. And so if we go back and look at our example, what we would do is we would start with that air at 72 degrees and we would extract heat out of it, the sensible heat. And you can see when we do that, the dry bulb lines we're crossing them. The air is getting colder and colder. And we would take that air down to 32 degrees. And we wouldn't go below that because of the risk of frost, right? So there would be a temperature sensor in the exhaust air stream that would modulate the speed of the rotor or open a bypass damper and allow air to spill around it and never let that temperature drop below 32 degrees. Well, all of that energy is being recovered and passed into the supply air temperature. And it works out if your airflow rates are balanced, then your temperatures are going to be balanced. So we were able to cool air from 72 degrees to 32 degrees. That was a 40-degree temperature drop. So we will see a 40-degree temperature rise on this side of the air. So we're able to take air from 0 degrees to 40 degrees, which is a significant energy savings. But it had the effect of only recovering 56% of the possible amount of heat. The device itself is designed to be able to do 80%, but we're actually modulating its capacity. You should never think that means that you get no energy recovery. It's flatlining your energy recovery. You're not going to get more than a 40-degree temperature rise. No matter how cold it gets outside, it's not going to help you be able to get more heat. Your device will just keep modulating itself down so that it never frosts on the device. Well, let's look at humidity ratios, right? So this is a sensible device. So we had air here at what we said was 72 degrees and 20% RH. And we're going to look at humidity ratio. So what's that? That's these blue lines that run horizontally across. And it is the measure of how much the mass of water vapor in the air to the mass of the air itself, the dry air. And we measure the water in grains. Now, grains is just a measure of weight or mass. There are 7,000 grains in a pound. And so this number is 40 grains, this is 60, this is 80. If I look at 60 grains per pound, what that's telling me is that this air has 60 grains of water for every pound of air that's in that. So any point along this line has the same number of water molecules on it. In our case, we started with air that was 72 degrees and 20% RH. It had about 23 grains per pound. And all we did was take the sensible heat out of this air. So there was no change in the humidity ratio because we never let the air get to saturated condition. So this is a constant humidity ratio process here. No moisture is added, no moisture is removed. The same is true on this side. We started with air that was incredibly dry. This is outdoor air, 0 degree air. 0 degrees can hold very little moisture. Actually have a very high RH, relative humidity, because there's so few, such a small amount of moisture before the air is saturated. And so there's only 4 grains in it. And we're going to take that air and heat it to 40 degrees, but we're still only going to have 4 grains in it. So this air is going to come into the building extremely dry, and will actually have the effect of lowering the RH of the whole building. So this is the humidity ratio in a winter application. So let's look at enthalpy. And enthalpy is the internal energy of the air. It's these red lines that you see going across at a diagonal, and we talk about it as BTUs per pound, right? So we have this energy source. This is return air that's going to be exhausted out of the building. Has a lot of energy in it, and we want that energy. We've paid to heat the air at some point. We want that energy back, And so what we're going to do is extract it using some kind of heat recovery device, rotor, the plate, a wraparound heat pipe, something, get that energy, and we're going to take it out of the air. And so we're going to recover 9.6 BTUs for every pound of air we're exhausting out of that building, and hang on to it. And we're actually going to pass that heat over into the supply air. And so we'll put 9.6 BTUs of heat into the outdoor air. And so we'll warm it from this very low enthalpy point all the way up to 40-degree air. And so we keep the energy in the building. This is why it's considered energy recovery. And so a lot of energy codes, including ASHRAE Standard 90.1, have requirements that you use energy recovery devices for your outdoor air, just because in the correct climates, this is a critical way to save energy inside the building. Now you'll notice these numbers are exactly the same, and it's because the two airflow rates are exactly the same. You can't. We're not destroying energy or getting rid of it. So whatever came out of one airstream had to go into another. If the airflows were not exactly the same, say the outdoor air was 10,000 CFM and the return air was 9,000, the BTUs per pound might change, but when you actually took into account the mass flow rates, you would realize that conservation of energy is being conserved, and that whatever you took out of the exhaust airstream was added to the supply airstream. Let's look at this device and see how it would run on a summer design day. Again, it's a 80% efficient device, and so we're into cooling recovery, and this time we're going to use air that is hot and humid. So it's 90 degrees outside, and we've got our dry bulb temperatures across the bottom, and we're going to use 75-degree wet bulb. So that's our wet bulb lines are these blue lines here, and so it comes down here, and that's our starting point. So this is now the outside air. In our return air is going to be 75 degrees and 50% arch. It's basically the design conditions of the space. That air is going to be exhausted out of the building. We've spent energy and condition that air to be acceptable to the people inside the building. And it's not an energy source to us now, it's an energy sink. It can absorb energy, and we have this hot and humid air outside, so we would like to use this sink before we completely exhaust it out of the building to help us precondition this outside air that's hot and humid. So we want to take advantage of this cold source, if you will, to do that. And here's what the process would look like. So the outdoor air, in this case, is going to get cooled. And it's going to get cooled from 90 degrees down to 78 degrees. It's 80% efficient, so that means we can get 80% of the way between this temperature gradient in here. This is 15 degrees here. 80% of 15 degrees is 12, and so we can cool the air from 90 to 78. So that's what's happening here. Now, if we take that heat out of the air, it had to go somewhere. It actually goes into the return air. So we're going to exhaust this air out of the building 12 degrees warmer. That's why it's going from 75 to 87. If you actually put your hand on the discharge of this unit, the air would feel warm leaving the building. And so we were able to pre-cool the air sensibly and help lower the load on the cooling equipment. Now let's talk about humidity ratio. This outside air is incredibly humid. It's 106 grains, and our return air is where we like to have it for indoor space. It's about 65 grains per pound. But this device is a sensible only device. It's not capable of changing the humidity. So we started at 106 grains and we'll end at 106 grains. Same here. That even though this air is drier and is capable of receiving water vapor, the equipment is only a sensible device. It has no means by which it can move water vapor from one airstream to the other. And in the summer, these conditions are actually quite close to each other, right? We're talking about 90 degree air versus 75 degree air. So sensible energy recovery in the summer doesn't have the same big impact you have in a winter climate. In the summer, what's more important to you is your ability to remove moisture. right? That outside air is significantly more humid, has a lot more water molecules in it than what we want inside the building, and so what we would be more focused on is a device that could remove humidity rather than a device that can cool the air. So, but this is the limitation of a sensible energy recovery device. So last thing we'll look at here is the change in enthalpy. You can see we're only able to change the outside air by 3 BTUs per pound. Just to remind you, that's these lines here, these red lines. And so we were able to, that's 3 BTUs per pound that is not going to be applied to the chiller or the refrigeration system to cool the air. And that heat was taken from one airstream and added to the other. But because it was just a sensible energy transfer and there was no moisture moved, it wasn't a significant change, but every little bit helps. So that's the end of this discussion. Thank you.